Thanks a lot. Great pleasure to be here in Sweden, my first time here. I'm really excited to be in the home of Swedish death metal. So big thanks to the SecT crew for accepting me to come here. So I'm going to be talking about forensic resistant data destruction. And the background of this work is, or the motivation for it is the security risk of the waste stream, which is something I think that we're all pretty familiar with, right? So when you have stuff that you need to throw away, a lot of times it contains secrets, and there's secrets that you would like to keep from your competitors if you're a business, from criminal organizations who can use it against you, or even just stuff that would be embarrassing and you just don't want the public to know about. And a lot of us here who are from the old school remember trashing. You know, that's how we would get phone company manuals and stuff like that, right? We'd go to their offices and we'd go through their trash and get their printouts and get cool stuff from them. But we're dealing with exponentially increasing volumes of data now. So it's not just printouts that are a risk. We're talking about terabytes of information that can be on a really small package. So here's a couple of examples of that. Really well-known research that's great to read up on if you haven't seen it, where people go and they buy printers and copiers secondhand and pull the hard disks out of them, and they discover that these machines are often forensically really bad about erasing their hard disks. So you send a document to it, it sits on a hard disk in the printer for a while, indefinitely sometimes, it gets thrown away and you can recover it. So all kinds of interesting information from there. And then a lot of things with a lot of data in them are going mobile. So autonomous vehicles, for example, have all kinds of proprietary information in them. If they crash or are otherwise recovered, they can have all kinds of things that you might not want public on them. I'm concentrating a little bit more on if someone actually actively tries to grab your data storage unit while you're still using it. So think a data center with some very valuable things on it, and you need to get rid of that data center in a hurry. Presumably you have it backed up somewhere else. So the goals of this work are a switch that you can flip that destroys the drives, leaves nothing standing for even the most advanced forensic analysis. At this point, you might be saying, well, hey, we're going to encrypt all our stuff. We're very responsible with our data centers, so it's no problem, right, if someone steals these hard disks. It can be a problem, because crypto is only as secure as the key. You can often unexpectedly recover the key from physical media, and once the key is compromised, everything's compromised. So we want something that, of course we encrypt stuff as well, but we want something that's going to physically destroy everything that can be scaled to a data center size. And we should always consider our threat model here. We're going to assume an extremely high capability criminal adversary in this work. So let's take a look at what's done industrially when people get rid of hard disks. When you decommission a disk, if you're a responsible disk decommissioner, then you degauss your drive if it's magnetic media, and then you crush or shred it. So here's an example of an industrial shredding machine with hard disks being thrown into it. Turns them into a nice little pile of metal chunks. Once again, here we have to predict our adversary. Highly funded forensic organizations, such as nation-state intelligence services, collect and exploit drives that have been physically destroyed. So I had a very interesting conversation with a guy who was on the weapons of mass destruction search team in Iraq after the American invasion in 2003, and he was under instructions from the NSA if he found any data storage units, no matter their physical condition, if they'd been crushed, whatever, he was to collect them and send them in for processing, because data could be recovered from them unless they were also burned. So if you're really paranoid, the way that you can nuke your data from orbit, degauss your drive, crush or shred, and then burn the remains. And then for the extra paranoid among you, separate those remains. Don't even put them in the same trash. But here are the rules for the work that I'm presenting. We get 1 U for our data server, times however many in your data center. 1 U above and below that server for whatever you want to put there. So that you can fill it with concrete for protection. You can put in hot gas extraction system, whatever you want in there. We got 60 seconds to go from the switch being flipped to everything being gone. We want to not telegraph our activities. We want to not set off the fire alarm systems that can also have results like sprinklers or halon systems that can cause problems. We want to contain our damage within our own equipment in case there's other things in the data center that don't belong to us that we don't want to destroy. In particular, nearby humans. We don't want to destroy them either, so we need to have some level of safety here. So a quick look at hard disk technology. I'm going to concentrate on spinning platters because that's still the majority storage in large installations, magnetic media. So if you look at what a spinning hard disk is made out of, platters come in two varieties. They're either solid aluminum plates, most common, historically speaking, or more commonly these days they're glass because you can make a much flatter disk and you can spin them at higher speeds without having vibration problems. So I'll concentrate on aluminum platters here because glass is really easy to shatter and break. Those platters are coated in an underlayer of cobalt, nickel, and iron. The actual magnetic alloy is a cobalt, chromium, and platinum alloy. And the layers are separated by a 4-atom thick layer of ruthenium, extremely chemically unreactive. So that explains why I won't be presenting any chemical attacks, was one reason. I'll also look a little bit at solid-state drives, but only one attack method on these because they're really easy to break. So the three attack methods I look at will be thermal, so heat attacks, kinetic, physical smashing, and electrical attacks for the solid-state drives. So our goal with a thermal attack is basically to burn the disk, to exceed the Curie point of the magnetic media, which is the point at which these aligned magnetic elements have their alignment all randomized, and so they're no longer readable. So for cobalt in a hard disk, we're talking over 1,000 degrees Celsius. So you have to get them pretty hot. So here's a few things I didn't look at. Just burning them with a torch is pretty simplistic idea. It turns out it's hard to do it in a minute because a hard disk is a big heat sink, and you'll see some of that later. I was really psyched to look at some flameless chemical reactions, but I couldn't find any that got hot enough. And then ovens and inductive heating. You can't really do it in 60 seconds unless you've got a giant unit, and in which case you kind of know it will work. So it wasn't a super interesting thing for me to look at. So the first thing that I thought I'd try is, well, you know, let's start this research. I've got a plasma cutter in my shop. Let's just hit the spinning disk with a plasma cutter. So plasma cutter is a really good way to dump a lot of heat into something really quickly. You know, you can cut through inches thick of steel if you have the time. So it really shouldn't have a problem here on the drive. And mostly I was just looking at the time involved and just what sort of a mess it made. And it turns out it doesn't make much of a mess. It takes about 40 seconds. And you see a nice little flame come out the side to tell you when it's done. As I mentioned, a heat sink sinks heat. This drive stayed hot for a very long time. So I repeatedly burned myself on this hard disk trying to get it open. That's why I'm wearing a glove there. And you can see it burned a hole through the top platter here. And you can also see, as the drive was spinning, there's some damage to the disk, but it quickly stopped spinning and thermally seized. If we take some of the platters off, you can see it burned all the way through. Nice job there. You obviously can't rely on it to keep spinning. You'd need an array of plasma heads if you were going to do this industrially. So that's what you would use your 1U above the rack for. Just put a nice little circular array. A very feasible method. So I was feeling good here, getting off to a good start. But I really wanted to sort of condense the amount of equipment needed to do this destruction. So I was thinking to myself, well, the center of these platters is aluminum. That's a very reactive metal. So if I can just pump an oxidizer in, I could generate some kind of a rig where I could pierce the disk when necessary and pump pure oxygen in, use a little igniter to start things going, and then maybe I could burn up the drive. So here is a little plumbed in with a little oxygen to give it a shot. And here we are in a real-time shot of pumping in some oxygen. You can see the igniter gets going there, and oxygen makes things burn really well. Here's a high-speed shot filmed at, I think, 960 frames per second. And you can see there's a little hole that I drilled to vent gases there, so you could see that spraying out of the hole. And Aluminum burns very brightly. Good pyrotechnic material as well. So that's, I had to stop this earlier than I thought I would because you can see the gas hose is melting and I was afraid of starting a dangerous fire in the workshop. So let's take a look inside and see how things look. It looks pretty messy on the outside. Opening it up, we can see just, this reasonably brief time period, okay, just a few seconds. We could, according to my rules, have 60 seconds, has combusted a lot of the drive. So I think this as well. Oh, here's an example. You can see out of all that burning, the drive reading heads are burnt, the read-write heads, and the disk itself has been eaten away pretty significantly. So using a hose that's not made out of plastic, I think you could consume enough of this drive in 60 seconds that this would be a very feasible method. So once again, potentially feasible. I'm feeling pretty good about my research here. But what I really wanted to get into with my thermal attacks, because if you mention this project to absolutely anyone in the whole world, they say to you, oh, well, everyone knows how to do that. You use thermite. And I'm like, okay, that sounds reasonable, right? But I want to try it. The military uses thermite in incendiary grenades. So we got military approval for this technique. One thing I really wanted to do was to make an injectable thermite slurry. So something that I could pump into the drive on demand with some kind of injector, set it off, be totally done with it. And we'll cut a long story short there and let you know that was not successful. Slurrifying the thermite is very difficult, and I tried a lot of different solvents, and it didn't work. But let's get on to what I did. What is worth showing to you. First of all, here's the thermite reaction. So this is basically a classic redox reaction where you start off with your raw aluminum and iron 3 oxide. This is the most common thermite anyway, and the oxygen swaps over from the iron to the aluminum. It produces raw iron, which turns out to be molten iron at these temperatures, produces a lot of heat. It gets up to about 2500 C, so we're well above where we need to be for our Curie point. For those who want to try this research at home, that's the ratio. It's very easy to make. You also don't need particularly good grades of chemicals. You can use just industrial grade, basically art supplies. You can make a good thermite with it. So I thought to myself, well, my slurry hasn't worked, but I need to get thermite in the drive here somewhere. And fortunately, 5 1/4 inch drives have a lot of room inside them where you can put stuff and the drive still works. So I opened up this drive, and there's even some unused pins on the bus, so I could connect a little nichrome wire there to act as an igniter. And there's my little baggie of thermite inside the drive. If anyone works for the customs agency and you find someone traveling with a lot of hard disks, perhaps you might want to take a look inside them. You can fit about 15 grams of thermite in there. And here's how it looks when it goes off. 3, 2, 1. Very containable, right? It doesn't make a bunch of sparks going everywhere. So that feels good. Here's what it looks like inside. And as you can see, it's made a big mess out of all of the control electronics there in the drive. And we open it up and start brushing stuff off. And suddenly this is not looking so good. That disk is looking kind of okay. And it's the battle with 15 grams of thermite. The disk has pretty much won here. Here it is fully cleaned off. So those platters, they've done really well. That big aluminum slug at the bottom of the drive has absorbed a lot of the heat, and the ruthenium layer has protected the outside from oxidation. So I'm going to call that a fail. But I'm not ready to give up yet, because actually if you look at military thermite grenades, they don't use raw thermite. They use a variation called thermate, which is thermite plus 30%, well, 70% thermite, 30% barium nitrate. And the barium nitrate produces gas that moves everything around, and it also makes everything burn a little bit hotter. So you can even get above 2500 C with thermate. And so let's take a look at that. Also, it happens very quickly, so let's take a look at a high-speed shot. Once again, not especially high speed. I think shy of 1,000 frames per second. But you can see the pressure that this is producing here. It's pushing a lot of stuff out through that gasket from the top of the hard disk. But once again, even though this is more sparks and debris than the plasma cutter produced, we could deal with that if it works. We can contain something like this. I think the camera has not great dynamic range, so it makes it look more crazy than it really is. But it looks nice. You could have a bunch of these for a celebration. So let's take a look inside, see how this performed.
Ooh.
All those little beads there are molten iron from the thermite reaction.
Yeah, that's quite impressive compared to the straight-up thermite. I guess there's a reason why the military uses this formula.
So there's a close-up of the platter, and so we've dropped a bunch of molten metal, as I mentioned, on the drive. And when we clean it off, we can see a few things. We can see that we've melted metal to the read-write heads. There's some delamination of the surface of the drive. That's a good thing. Pretty sure that there's nothing going to be readable from that area. And we've actually welded the two platters together in that place. But the rest of it kind of looks okay. We can't really guarantee that we've got to the temperatures we need to get at that point. So once again, we have to call this a fail. But I am not ready to give up on thermite because everyone says thermite's the way to go, right? It turns out there are other types of thermite, not just the iron aluminum kind. For example, copper thermite. Copper thermite used aluminum as well, but copper oxide instead of aluminum oxide. Once again, if you want to try this at home, 4.4 to 1 is your weight ratio. Copper thermite is a very aggressive thermite. Thermites have a reputation for being difficult to get going, but not this one. So here we are, we're doing the same thing. I've got my little baggie of copper thermite. It's also around 15 grams inside the drive. And this is a high-speed shot. Once again, same camera, about 960, I think, of that 15-gram test. So keep watching here. You can see the top plate of the drive coming off down there. But keep watching, because it's not quite done yet. There's the hard disk. So that's gone from a standing jump on a concrete block with the force downwards to bounce it up several feet into the air. Also, that cloud was incredibly toxic and terrible, and we all had to run outside and assure the neighbors that there was nothing to see there. So really beautiful effect. That's the top plate of the drive. So you've got these just awesome psychedelic patterns produced on the metal. And here is the drive itself. And I wonder what's making that scratchy thing. Anyway, things are looking pretty disgusting here, right? Like covering electronics in a thin layer of copper seems like something that would be bad for them. And we can see actually from this shot little beads of copper on the platters and then also attached to the outside of the drive. So let's use our incredibly scientific cleaning method here to see what happens. And oh man, it's getting pretty clean there. So once again, there's lots of little bits of copper stuck to the drive. It didn't get completely clean, but I feel like if you were the NSA, right, that's not going to stop you. You could clean those things off somehow. You mechanically remove them and still be able to read some magnetic information from the drive. So we have to say infeasible, but fun. But I'm still not ready to give up on Thermite. Because everyone says that that's the thing to do, right? Ask anyone. So I said, well, we've got all this space inside a 1U rack. So maybe we just need more Thermite. So I made a mold that, so this is a ceramic refractory material that I cast to exactly the same size and shape as the hard disk, with a cavity inside it that I could fill with a lot of Thermite. There's the hole. You can see that it fits precisely on there. So I could fit about 250 grams of Thermite in there. So we're more than 10 times our original effort here. Regular iron Thermite, and I've got everything clamped down to just try and keep things contained. Once again, non-real-time, high-speed shot. Containment was not successful. So, if we're going to do this in our data center, we're going to have to really think about how to contain it. But, these are things, it's engineering, right? If it works, we'll put in the effort. Incidentally, I was doing this in a friend of mine's workshop, and he has a large rug on the floor, and it set a lot of the rug on fire. So I apologize to him for that. You can see that the ignition hole at the top there, we've still got like a jet of flame coming out of it, right? There's still a lot of stuff reacting inside that cavity. It's getting pretty hot in there. So let's open it up. So, it's done to perfection in the oven here. Here's what it looked like right after taking it out of the block, and you can see a few things. You can see that we have melted a hole in the top case of the drive, and you can see all of those lumps up the top there of formerly molten iron that's congealed. So we've got things pretty hot in there. Here's after we take off the top case, and we can see all the electronics is completely melted. But once again, the drive stays pretty clean. We've got it hot, but we can't guarantee that we've got it hot enough for long enough. So we have to say, most likely unreliable. So if you have this conversation with people and they say, oh yeah, Thermite your drives, you can definitely do it, right? You just need a lot more than you think you would need. And probably hard to do it inside an enclosure, because hard disks, there's a lot of aluminum in them. So that's it for thermal. I moved on from there to kinetic methods. So our goal here with a kinetic destruction of a hard disk is we want to deform, spindle, mutilate the platters, and basically we want to make it extremely difficult for someone to mechanically scan those platters and recover any useful information from them. By itself, it doesn't destroy any of the magnetic information except for where the material actually bends and fractures. So you'll want to use this in conjunction with a degaussing method of some sort. So once again, there are some things that I didn't explore here, such as using a big hydraulic cutter or crusher. You can get these things. You can just buy them for destroying hard disks. They mostly come down vertically, so I thought, well, you could make a horizontal one and fit that in your 1U rack. I didn't do it because I knew it would work. You can get small hydraulic cylinders, and it just wasn't a very interesting thing to do. And then also high-pressure cutting tools, like the plasma cutter one. We could do it, but packing all that stuff into your server equipment is a little more difficult than packing in a plasma cutter, so it seemed impractical enough not to bother with. But the first thing, my first idea that came to mind, because I've used these type of nail guns before that use a 22 caliber propellant charge. So they're basically like a little gun that fires nails, and they are for driving nails into concrete. So I thought, well, this will definitely work on a hard disk, right? So Here I'm trying this on a hard disk at 480 frames per second. Sorry, on a piece of concrete, showing that it blasts straight through a concrete block. It's so fast that you can't even see the nail come out. So I'm thinking this should go through a hard disk. So here's a spinning drive that I milled the end off, so you can see the plates, the platters inside while I fire the nail gun. And here's some high speed of it coming out, and sure enough, it goes straight through with no problems at all. So I thought, that's cool. But while I'm at it, the guy who lent me the 22 caliber nail gun also lent me a pneumatic nail gun. And I thought, wow, I don't know if that will work, but hey, let's give it a try and see, because pneumatic tools are really easy to deal with. And we could easily have air hooked up to our data center very safely. So here's firing the pneumatic nail gun through the same hard disk. And that also goes through with no problems at all, which was surprising to me. I thought, oh, you know, it might get through, but yeah, it goes through very easily. And you can see the results there about how significantly warped those disks become. They get basically squished to each other. And I think that's a pretty feasible way of destroying things. Like, you could very easily imagine a system that had a ring of multiple nails and a pneumatic platter there. You just hook air up to your data center as well as power, and boom. So that's kind of cool. Wasn't expecting things to work so quickly, because what I really wanted to work on here was high explosives. And this is something that I had wanted to do for a long time, not just to do with hard disks, but I'll say a bit about this in a second. This is a project that I'd been needing a reason to do. So let me get it out of the way right away. There's no doubt that we can destroy the hard disk with high explosive, right? Of course we can. Not only does it smash, it also gets hot, so we have thermal factors. There's actually a type of welding that people do called high explosive welding, where they put a flat sheet of explosive against two pieces of metal, and it presses the metal into each other and heats it up so much that they weld together. So my goals here, number one, can we confine our high explosive? Because that's the interesting part. And secondly, I really wanted to experiment with some new techniques. And in particular, once again, something that I'd wanted to do for a long time, because I thought that it was possible to do, and I had not seen anyone else do this, was to 3D print explosive charges, or directional explosive charges, prior to this work, there was no open source literature on this. Why would you want to 3D print high explosives? Well, high explosives, you have a lot of energy in a small package, but if it's just in a uniform package, that energy goes in all directions. And so you waste a lot of it if you want to direct it against a certain thing. So for example, this is a shot that I took at the Pyrotechnics Guild convention this year. These guys want to destroy this rack. And to do that, they have to use a really big explosive, because most of that explosive force is going to be directed to the ground and to the sides and going to be completely wasted. So everyone was really happy that this worked, because it wasn't clear that it was, and you needed a huge bomb.
Somebody got that on film.
We have a very limited amount of space here. So what we want to use is an effect called the Munroe Effect, or you might know it by its sort of more common name, the shaped charge. So what this is a block of explosive that actually has a cavity inside it. That cavity is often conical, but it can be linear, a triangular groove in the material. And what this does, sort of counterintuitively, that groove or that conical shape actually concentrates the explosive force within that cavity. So when your explosive goes off, that cavity directs a lot of the energy towards itself, and you can form a jet, basically, that cuts through the material that's underneath it. And so that's how high explosive anti-tank rounds work, and it's also used a lot in some industries, which I'll get to in a second. If you line that cavity with metal, you can form a what they call an explosive formed penetrator, so that you form a jet or a slug of metal that moves at the speed of the high explosive very quickly through whatever's in its way. So there's an example of a commercial charge showing that liner effect, the high temperature metal jet. The metal you want, if you're doing this, is something with a high density and ductility. So copper is a very common liner material. If you can afford it, like the military, then tantalum is another one. So it's not just for capacitors, it's also for high explosive penetrators. So here's an example of a commercial high explosive penetrator. And this is used in the oil well industry, because what they do, this is called a downhole perforator. So if you're drilling your oil well, you start drilling down, and then you start pushing pipe down around the drill, and you drill to the bottom, and the pipe that you eventually push down the center is sealed at the bottom, because you don't want all this oil coming up while you're doing the drilling and while you're trying to clean everything up. Then when you're done, you sand some of these things down, and they punch holes in the metal and let the oil out so you can start slurping it up. So what we see here at the top, there's a little a hole in the metal shell that the blasting cap goes into, or your detonation cord. And then on the inside here, you can see the liner. And then that ring of metal on the right-hand one is a standoff, because sometimes, a shape charge has an optimum standoff distance to allow the jet to form. So these are some commercial ones. You can gather the size. They're on my hands, so they're very small, but very nasty. So here, I'm setting off 2 of those with the cavities pointing up. So you just got a glimpse there. If we freeze frame that, you can see the two jets forming and moving at an extremely rapid pace, at thousands of meters per second. This is a quite amazing shot, because we see our jets, but if you look down in between them, the detonation cord that I'm using to set those off hasn't ruptured yet. So that high explosive shock wave has gone through that cord. You can see this blast from the blasting cap, but the cord itself has not ruptured. So this is kind of an amazing still to have got from a regular non-high-speed camera, to be able to see those jets forming before the detonation cord has itself ruptured. Crazy. I was amazed to see that. So let's start off by trying one of these on a hard disk. So we've got it there taped to the side. You can see blasting cap, det cord, penetrator, or perforator rather. And here we go, real time. So, you know, thing flew away. We'll have to deal with that. Watch for the upper left to see part of the drive flying away. There it goes, but not as far as you would think, right? We can contain that. And here's what it looked like when we went and collected it. So you can see it just sliced through that drive like it was just made up of a soft material, like a cheese or something. The platters have moved on, but we found them, and same deal. The jet just cut straight through them like that, which is pretty neat for a tiny little thing. Here's all the pieces that we found of that hard disk. So one piece missing, we didn't find that one. But they're sitting out there on the steel plate, the 1/4-inch steel plate that we were performing the experiment on. What's that? That was underneath the hard disk. It's a little hole. That's a close-up of it. That's a close-up of the other side of the plate. That's the ground underneath it. And that's the piece of wire we used to measure the depth of that hole. 15 inches is, what is it? 47 and a half centimeters or something like that. So we're going to have a challenge to confine a blast of this type. So here is the parameters that we have for designing a shape charge. For a given explosive composition, there's kind of a linear inverse relationship between the angle of that cone, the steepness of the internal cone, and the velocity of the jet that you get out of it. Very, very close to linear there. So we have that piece to control our parameters, that apex angle. We also have the distance of standoff between the charge and the thing we want to cut through, and the height of that cone. So those three parameters. And of course, we want to do this digitally. So we want to 3D print this explosive. So you want to make a 3D model with parametric abilities. We have our good friend OpenSCAD, my favorite open source modeling tool, where you basically write functions to describe solid objects, and you can pass parameters to those functions. So I designed parametric models in OpenSCAD. Anytime you develop a new 3D printing process, you have a lot of materials handling issues to deal with, right? Like if you just want to move to a different plastic in a normal 3D printer, then you have to figure out all your temperatures and different heights and so on. This is even more of a problem when you have a material that you might suffer from internal voids, right? So we want solid high explosive blocks. We want to be pretty sure there aren't little internal cavities or kind of weirdness to it that might mess with what we're trying to do. So that can be tough to 3D print directly. So I thought to myself, well, I don't want to deal with all this extrusion and dealing with the need to support the fact that I want an internal cavity. That could be a lot of work and may not ever be successful. But maybe I can shortcut this by 3D printing a really thin-walled plastic enclosure and then filling it with a self-compacting explosive, a liquid explosive that will make sure that we have no voids, and that plastic liner is just going to completely vaporize as soon as the explosive goes off. So once again, this is the first open literature 3D printing high explosive geometry process that I know of, but I still had one thing I needed to do. I needed to get my hands on a liquid explosive. So I did some research, and I found there's a commercial 2-part binary explosive, which you can buy if you've got lots of money, but I preferred to do it the hacker way and reverse engineer it and make it myself. So I'm calling it Felix, which stands for Field Expedient Liquid Explosive. It's similar to some things that you can buy in the United States called Tannerite and Kind Pack, which is just one of these weird things about the United States, right? Like if you have certain things that you feel like it's your right as an American to be able to do, like such as shoot at high explosive targets, then that's pretty protected, and in the United States you can do that. So you can buy this stuff specifically for making targets to shoot rifles at and have it explode, and yeah, they make a big bang. And the law is really weird, right, in the US about this. Like, you can buy this stuff, you need no licenses or whatever, but it's only legal to set it off by firing a bullet at it. If you set it off any other way, then you're breaking the law. But as long as you're using it as an exploding target, you're cool. So they're basically based on a nitrate. So these high explosive target ones, are based on ammonium nitrate that's been sensitized with aluminum powder. But that's a solid, so I want a liquid. So a good liquid to use in high explosives is nitromethane. And then same deal, you sensitize it with aluminum powder, but the type of aluminum you use is really important. It has to have a certain particle size, and it needs to be coated with stearic acid between 1% and 2%. And so it makes it all weird and clumpy. But there's some good things about this. You can ship it separately, and it's only a hazmat. It's not a high explosive until it's mixed. It's totally legal to own both types until you mix it. Then you need the permits. Here's the stoichiometry. So nitromethane by itself is a high explosive. It will decompose into carbon monoxide, water, hydrogen, and nitrogen gas, but it's very insensitive, super hard to set off. However, once you mix in some aluminum, it's sensitized dramatically, and the aluminum reacts with some of the water that the nitromethane decomposition produces, and produces more hydrogen gas and more energy. So it adds energy to the reaction. So first of all, I decided to do an annular shaped charge, so basically a linear shaped charge that's wrapped around into a ring, so a circular groove here. So there's the OpenSCAD model, there's the 3D printed shells, and Here we are mixing up some Felix. 60 grams of Felix was what filled up that shell. And then with a little plastic standoff and strapped to a hard disk, let's give it a shot. Once again, hard disk didn't move too far. That's a good sign. We've directed a lot of energy downwards. Here we are, high-speed shot. And hard disk comes to rest. Interesting that copper thermite moved it further. And here's another one of the same charges, because we did this test a few times. That one went a little further. So here's what the drive looked like after recovery. So we learned a few things from these drives. Number one, using way too much aluminum. So the exact stoichiometric mixture is completely overloaded with aluminum. You don't need to use that much, which saves some money. We've stripped all of the platters off the spindle, and we've got some high explosive welding of the platters afterwards. And the shape charge has not cut through all of the platters. It's only cut through in that one place. And that one place matches where the blasting cap was placed originally. So what's happening here is that the blasting cap is setting off the shape charge exactly how we want, but that propagation of the explosion isn't going around the circle the way we want it to. So doing that ring-shaped shape charge is not a success. So I moved to a radial shape charge. So a bunch of grooves heading outwards from the center. And then I made a lid for it as well to hold the blasting cap and hopefully contain everything to allow that shape charge explosion to propagate directly downwards in all directions. There's the printed model, using a little more Felix in this one. There's more empty space to fill. And then instead of a detonator directly, I'm feeding in a ring of 80 gram det cord. So once again, starting it off all the way around that circle. Here's how that looks in real time. And at 960 frames per second. So, we're going to have some confinement challenges here. But that's part of the research. We got a good long shot here with a GoPro at 120. So, I want you to keep that in mind, right, what you're seeing here. Not many big pieces left of this. So the circuit board has all the components completely stripped. Here's what we could find of the drive, seeing a lot of cuts and also some explosive welding of the platters. So, we're doing pretty well here. Obviously, we can do a little bit more work on the geometries, but I think we've got a bigger problem here, which is our blast suppression. So we need to couple the blast to the hard disk, right? We want to direct our energy towards the thing we're destroying. We want to decouple that blast from the surrounding equipment, right? We don't want our energy there. So we keep our explosive against the hard disk, and then we want to separate the explosive from the exterior of our equipment with some kind of damping material in between there. So we need some material that is going to absorb a shock force. And so maybe we want some kind of matrix that alternates compressible and incompressible material, like some kind of a foam. We want it to be cheap, and we want to be able to pump this into our equipment when we need it, right? We don't want to have to fill our equipment with stuff that's going to make maintenance annoying when we're not destroying our stuff. Turns out there is a magic ingredient like this, which I learned from an explosive engineering instructor. It's regular shaving cream, right? It comes in a can. When you press the nozzle, you get this great foam that remains as a foam for a little while, long enough to shave with anyway. So let's do some testing of this. We got, in this case, just straight up det cord, not bothering with the shape charge because we're just testing the confinement, and our shaving cream. put it all in a box, and fill it up, and let's see how it goes. Right? You guys remembering that earlier one from the GoPro with the giant explosion? This looked a little bit different from that. Here's some frames that are the first frame of the explosion from all of the cameras we had pointed at this. So, I scrubbed through and found the first explosion frame. This is our damped version. This is the undamped version. This is from our close-up camera. Pretty different. And that difference is accentuated by the fact that these were both det cord only shots, right? Not Felix shots. So the one on the left had 2.5 times the amount of explosive as the one on the right. So that's pretty crazy. So let's do it. Let's do this whole thing for real and try and see how it might look. So we've got 75 grams of Felix in our shape charge container. We've made a little 1U rack simulator by welding some angle iron onto a piece of steel. Set up the blasting cap, fill it with foam, stick a piece of metal and a sandbag on top, right? So if we're doing this for real, we could have a sheet of concrete or whatever, but we're just field expedienting this thing for the sake of quick research. And here we go. It's like almost anticlimactic, right? Here's the high-speed shot. Certainly, things are still moving around, but we feel like, with the right kind of engineering here, we could definitely confine this. Here's the steel plate that was on top. It's put a dent in it, but it hasn't made a big hole. The sides of the rack simulator did not fare as well. They were bent outwards, so you'd need a little bit more reinforcement. We've got a little imprint of the hard disk on the plate there, but not too bad. So with the right amount of engineering effort, it just might work. So last method is electric. And so here's where I wanted to concentrate on solid-state drives. My goal here was you're in a piece of equipment that's plugged into power, so you've got this power source that's already there. So can you use that against the media, particularly your solid-state drives? Once again, there are some things I didn't look at. Degaussing, we know that works on magnetic drives. Probably not effective on solid-state drives. Exotic RF or EMP and so on like that. Didn't look at it. Would be definitely interesting to play with at some point, but that's not what I did. Once again, I wanted to concentrate on SSDs, and so the first one that I thought of is, well, what about just an electrokinetic attack? So to use an exploding bridge wire, which is what's used in certain kinds of detonators, like, for example, nuclear weapons, where you basically pump a ton of high voltage, high current through a wire, and it explodes at a high detonation velocity. So here's an exploding bridge wire setup that just has a big capacitor we charge to 15,000 volts, and I'm going to use this against an unfortunate flash drive. I didn't want to buy a lot of expensive solid-state drives to test on, so thank you Conference Swag, thank you MathWorks. I took a whole bunch of MathWorks flash drives, and that's what I'm using here as my substrate. So here we are. This is what the bridge wire looks like.
1.
So everything happens very quickly.
Ooh.
That wire explodes dramatically when you dump the power through it. Here's a high-speed shot at 960. And whew, it's gone. So once again, you can set off explosives with that. You can use it like a detonator. So let's wrap it around a flash disk and see how we go. How much force can we couple to that?
3, 2, 1.
All right, let's take a closer look. We moved it, but we didn't do a lot of damage to it. And you can see that here. The top surface is totally undamaged. The bottom, we did decap the microprocessor on that flash drive, so it definitely got a punch. But we can't say that this is in any way a reliable method of destroying the data that's on that top flash chip. So, okay, how about we attack the chip directly by sending our high voltage spike right to its power source? So we'll raise the ground, even if there's some internal circuit protection on the power line. There probably isn't on the ground. Pull that ground up to a few thousand volts. You may have seen, by the way, in recent times, in the last couple of years, these like USB killer flash drive things for sale, which have like a bunch of capacitors inside them, and you plug it into a USB port, and they charge up and then discharge at once and destroy the computer, or at least part of the logic board. So I did this before those were released, but now they're a product, or you can build your own. So let's wire this up, see how it looks.
3, 2, 1.
Closer look. 960. Bang! There we saw some pieces fly off, so that's looking pretty good. Sure enough, when you take a closer look, that chip has been blown right off the circuit board. All of its connection wires has been ripped out. It's partially decapped and snapped in half. So that seems like a potentially feasible way to destroy a bunch of flash memory, provided that you are willing to have a custom piece of rack equipment that has a large high voltage line into the ground line of your drives. So I think that's potentially feasible for SSDs. One thing that I wanted to just show you guys, because I thought it was super cool, and I feel like you could potentially do it on something with a metal case, so such as a regular spinning hard disk, is inductive defamation. So if none of you know any mad scientists, this is a classic piece of mad science equipment that people like to build called a can crusher. So what happens is you have a coil wrapped around whatever you want to crush. You dump a huge amount of current into that coil, and it generates a very rapidly expanding magnetic field that induces a reverse field in the can. The coil gets forced outwards from the Lorentz force. The can gets forced inwards, and it all happens really, really quickly. So this is at 2,000 frames per second. It still happens basically faster than you can see. Here's another shot of this, 2,000 frames per second. There's no contact between the coil and the can. The coil is just wrapped around it, and that can just gets crushed and cut in half. If you really want to see it happen, you have to shoot it a lot faster. So here's at 100,000 frames per second. To press the button. So 100,000 is a lot of frames, right? The whole time we've been watching this is this stuff is the action that you've seen there has taken place in less frames than at normal speed would have been taken to record what I'm saying now. So that's a cool thing I wanted to share with you guys. I didn't get to try it on a hard disk because the necessary power levels are unknown to crush that giant slug of aluminum on a disk. But physics is physics. If you had a big enough system, you could do it. So here's a quick summary of what I presented. If you would like to implement this, your most feasible methods in thermal are the plasma cutter and the oxygen injection. So kind of the low-tech methods, right? The kind of home hobby methods are more effective than your exotic materials like thermite. You may need to build some kind of a complex injector to punch a hole in the drive, but you can do it. For kinetic, the nail guns work great unless you think that the NSA is interested in you, in which case you should do something as well to a thermal or magnetic attack on your disk. And the damped high explosive could really work. But you will need to have a pretty solid barrier both above and to the sides of your equipment. And then the electric attack, the high voltage power spike appears to work great, but there's still a really open field on SSD forensics resistance, right? Like how much damage can you do to an SSD and still recover anything from it? So I can't guarantee to you that, again, if you're a person of interest to the NSA, I cannot guarantee that your liberty will be preserved here. And on that topic, I wanted to just close out with this notion of mobile solutions, right? So here's an example from the military world. This was an American drone that the Iranians captured, and they claimed that they spoofed GPS and forced it down. Probably not true, but one way or another they got hold of it, and also whatever interesting hard disks and so on were inside it. So there's obviously a military application for a mobile thing. And then I'm sure I don't have to remind people here about the sort of standard modus operandi now for capturing criminals who operate darknet markets, right? It's to capture them when their computer is unlocked and they don't have to break any encryption. The computer's already unlocked. There's various mouse jigglers and things like that that keep the computer awake while they do all their forensics on them. So I just want you to consider this scenario to close out. Think RFID proximity. As a Mac user, it made me feel really bad to blow up that Mac, but you know, sometimes you have to do things for art. So thank you very much. I've come in just shy of the hour, so I hopefully will have time for a couple of questions.
Yeah, first of all, I think we are in two different worlds when it comes to the word feasible. You seem to use that in a different way. And the last part, I'm not sure if I wouldn't sit with that thing in my lap, arm like that.
It's true. You have to really
You have to trust your shit,
your
right?
coding if you're going to implement something like that. Also, a very small amount of explosives in that. There was that was actually a little piece of det cord, that same 180 gram, same 80 gram det cord as with the containment experiments, and it was a piece about this long.
Wow, all right. Also, I just got the feeling that I wish I paid more attention in chemistry class. Maybe I would do been doing something like that. How about phosphor grenades, stuff like that? Have you looked at that?
I did not do anything with phosphorus, not for want of, not for not wanting to. I had actually tried about 2 years earlier to get my hands on some white phosphorus for a different reason, for a different series of experiments. Phosphorus is actually just a difficult thing to deal with in the United States. Red phosphorus is controlled by the DEA because there's one particular methamphetamine synthesis that uses a phosphorus component to it, so you can't just go and buy even red phosphorus. White phosphorus is even more difficult to get. It's classified as a chemical weapon. There are no United States-based suppliers for it, so I talked to a professor at MIT who specializes in phosphorus chemistry, and he said even he, in his lab, to get hold of white phosphorus, had to order it from some sketchy supplier in Ukraine, and he had to go down to the docks and meet it, when they offloaded it off the boat. So very hard to get hold of, so I wasn't able to experiment with that. It's also very toxic, so as far as burning things go, unless you're prepared to take some pretty serious risks, I would say stick to the thermite for your home pyrotechnic experiments.
But on a theoretical plane, I don't understand the chemistry, but would it be useful? Would it be helpful?
It wouldn't get as hot as the good things about phosphorus is you don't have to try hard to ignite it. It basically ignites itself in contact with air, and it produces extremely acidic oxidation products, phosphorus pentoxide, so it's going to chemically corrode things as well. But I think if the thermite didn't work, the phosphorus probably wouldn't either, and it would be very hazardous to install.
Yeah, you're the one redefining the word, feasible. So.
Yeah.
We got questions from the audience on this. Yes, we do. And there's a microphone. Let's take that one first then.
Hi. Did you consider anything about both environmental issues and also toxicity and stuff like that while doing your experiments?
So not really, especially not doing the copper thermite in my friend's garage. It was sort of this toxic cloud was something we weren't really expecting. But yeah, not really. The high explosive, as far as high explosives go, that's a really non-toxic explosive. I forgot to mention nitromethane. A lot of people would be familiar with that if they involved in auto racing, because high test auto race fuel is nitromethane, and also model aircraft. A lot of model aircraft use nitromethane as fuel. So it's something that's like, it's a hazmat. You probably shouldn't drink it, but it's not something that's like a super toxic thing to deal with or super environmentally unfriendly. Whereas other high explosives, like the explosive used in plastic explosive, is pretty toxic. So, this is kind of a fairly green way to go about things, explosives-wise. And yeah, I didn't really think about it the other ways. But your basic kinetic methods and thermal methods are very environmentally friendly, right? Like every shop has compressed air and a plasma cutter.
Have you considered using the thermite in order to heat the oxygen so that the oxygen reaction will be a little bit faster, so you can use some component like hydrogen peroxide?
Yeah, so the question about using thermite as the igniter, it's sort of the reverse a way that you would want to do things, because thermite can be quite tough to get going, and you don't need anything to get, in a pure oxygen environment, even a spark is pretty much going to get things going, right? Like there was, the example that most people know really well is the Apollo program fire, where they were using a pure oxygen environment, and just a small spark destroyed the entire capsule and killed 3 astronauts. So you don't need much to get it going.
Okay, just as a follow-up, how about component-based reactions? Reactions on which you produce the oxygen instead of creating the pure oxygen atmosphere by injecting the oxygen into the hard drive?
Yeah, so the question, using a reaction that produces a lot of oxygen. Actually, this is something I learned only recently. When you fly in a plane and the oxygen masks drop down, in many cases, the oxygen supplied to those masks is not from a bottle of oxygen. It's from an oxygen generator that uses decomposition of something like potassium chlorate. So it's basically a pyrotechnic device that's producing the oxygen in an emergency, and that's why they're small and they only have a couple of minutes of oxygen for the passengers to allow the pilots to get down to a safer altitude. So you could do it that way as well. So if you were going to implement that in a real data center, you could have a bank of pyrotechnic oxygen generators to generate your oxygen, just as you can on an aircraft.
They would generate a lot of heat as well.
They do, yeah, and that's why they keep them small. Actually, the reason I learned about this, one thing I do in my spare time sometimes is read about famous aircraft crashes. And I was reading about the EasyJet crash in the Florida Keys, and that was caused by, in the cargo area of that plane, they had dumped a whole bunch of pyrotechnic oxygen generators without their protective caps. And during the takeoff, one of them had gone off and started an unrecoverable cargo area fire. So they are something you have to be very careful with.
Okay, I have a question. Did you ever consider having an alternative reading head or something that would shave off the film on the discs, like a lathe or something? I mean, you have a rotating disc, motor, everything. Just shave it up in one minute?
Yeah, so I didn't explore a lot of those other kinetic methods because Deviant Ollam and Bruce Potter, this was follow-on work to stuff that Bruce and Deviant had done, or I was inspired anyway by some work that they had done and presented at DEF CON a few years before. And so they had looked at using a lot of drills and shop tools and stuff like that to strip the drive. And they had also looked at chemical methods. So that was one reason I stayed away from them, because they were just not very successful using those methods. It turns out, these methods will all work given time, but 60 seconds is not a lot of time.
Yeah, but then you kind of fight the shell of the hard drive as well. If it would be built in from start, I mean, the reading head would just do like a old record player, kind of destroying the data.
Yeah, that's a really interesting idea. And since doing that work, I've talked to people who worked on this kind of stuff for the military. So they basically, for drones and stuff like that, where you don't want a disk to fall into enemy hands, they have funded work like this in the past. So if you're designing the thing from the ground up, you could imagine potentially a market for a hard disk that's got a built-in kill switch, a mechanical kill switch of some sort that will, you send it some special bite of death, right, or whatever, and it will flip the drive head or whatever and cause physical destruction. You need to be a manufacturer to take advantage of that. But that would be a cool product. That sounds like something that I might buy.
Yeah, they're waving down there. We're over time. I'm sure there's more questions, and I'm sure there'll be year-round.
Hit me up tonight. We can talk about all kinds of destructive things.
But I really have, really, a big thank you, Zoz.